Okay, so we're doing a line integral. The formula for it is you're integrating over a vector field. That's important. You could do it over a scalar field. You could do it over a vector field. If it's a vector field where f function is a vector, you're doing an f dot product with what they term ds of vector. If you're doing this is for a vector function or a vector field. If you're doing a scalar function, like instead of a vector as your output here, you have something like f of x, y is equal to x squared times y, where for every point you plug in, you get a scalar, not a vector. This one is a vector, you get y comma y, but here if it's scalar, you have a different form of it. You have to do f of x, y, that's again a scalar, and you've got a dot product with the magnitude of it, so it's a scalar times, that's regular multiplication, by the way, scalar times a scalar. Here it's two vectors dot product, so there's a distinction. I don't have time to get into it, but be conscious of that. Two different types of line integrals you may be working with. Here it's a vector field, we're following this. You do have to understand what the ds is. The ds is, I forget how they write it, it's r prime, or no, he's not using r, he's using c. So c is going to be his curve. And so what you're going to be doing is the vector form of c prime dt. That's equal to that ds. So it's a generic form where you integrate with respect to dv. You're doing over a volume of a solid, and then you have to decide how you're going to split up that dv into dx, dy, dz, or cylindrical or spherical. Same idea here. This is a generic form that you then have to do if you're doing a path. You have to write out that path like that. So we're going to be doing that times f of x of t, y of t. So that's what we're breaking down. Good dot product right there. Shit. Let me write it down. So again, this is a condensed form. F is that function f of x, y, and we're going to be interpreting it as x of t, y of t, because we need to read this as in terms of a parameter. So we're going to parameterize the curve and rewrite this integral in terms of a single parameter, t. It'll be an integral in one variable, t. So we're replacing x and y with their parameterization, which I have not done yet, dot product with, and c prime of t, dt. That's what that is. It's a little chunk of that pathway. And you need the derivatives, some of the direction, and a little piece of t. And then we'll be integrating from a to b dt, where a and b are the starting values of t and the ending values of t. So that's what we're going to be doing, but it requires us to figure out how we're coming up with this x and y, which is a parameterization here. So it's all based on this path, which is on the curve y is the sine of x, but we need to parameterize it. One generic way of parameterizing curves is to replace x with t. So there's two ways to write it. I can write it as c of t in vector form like that, or I can rewrite my two coordinates separately. And what I've done so far is I've let x of t be t, so I can set it there, or I can replace it into that first component. And then I need to express y, and for it to be along this path, y has to have a very specific relationship with x. Specifically, y has to be sine of x. So y of t has to be sine of that. So a basic parameterization, which may not work, it may not make things simpler for you, and you might have to do something else, is to just set t to be the independent variable x, and then that'll be the function, the same function that makes up that curve in terms of t. But anyway, that is what I'm going to use. It does work here pretty nicely. And I need c prime of t, so let me go ahead and do that. Oh, sorry, and that's a vector, so I'll just reform. These are scalar functions because they're just going to give individual values, but that's combining both in a vector. And c prime, the derivative, will be 1 and cosine of t. Okay, and I should have mentioned an important aspect of this. What are my bounds for t? So I'm letting x be t, and then y will be sine of t, and I want to let t range from, so I can focus on the x, I want to let t range from 0 all the way to pi. In that order, going from smallest to largest, the usual way, because I'm going to talk about reversing the direction of it. This is going that way, so we're going to let t go from 0 all the way to pi in the usual positive direction. Okay, so what am I doing here? I'm ready to go. I'm going to write out this integral in terms of t. My function, my vector function right up here, y comma y. So that's going to be y comma y, but I want to express it in terms of t, so y comma y. It's sine of t, which is y, comma sine of t, which is y again. That's my yeah. It's coming from that. Yeah, I was going to write it above so you can see it clearly, but anyway, dot product it with c prime of t, right there. So you have a dot product, and when you do the dot product, you get a scalar integrand. And no, that means you can then, which will be a function of t, and you'll be able to integrate with respect to t, just use your integration from there. It's a setup that's the issue, and coming up with a parameterization that is sometimes the issue. And I'm going to let t range from, this is my t, is my variable integration, t goes from 0 to pi. And that's all I'm doing. Okay, so I'm going to multiply it out. I'm going to get sine of t plus sine of t cosine of t. That's two separate techniques for those integrals. I'm not spending too much time doing it, but antiderivative of sine is negative cosine. And that one is going to be a u substitution. I'm going to let u be equal to sine of t. Then d will be cosine t dt, so then I'm just going to have 1/2 u squared. You can check it. Bring the 2 down, cancels out, I'll get sine t, derivative of that will be cosine t. Anyway, that's what I'm going with. 0 to pi. Plug it in. My antiderivative at pi minus my antiderivative at 0. Okay, cosine of pi is -1, so that's a positive 1. That's 0. That's going to be plus 1. And that's going to be minus 0. 2. That is the line integral. And what it's doing is it's basically doing this dot product. So the idea is if this is a force field, but your path is going that way, then the work done by that force is force dot product distance. So you're basically looking at little points in time where you're looking at a point moving along that path, and it's having a force being applied that way. Let's say capital S stands for the force, but your direction, based on where you're at in the curve, might be going that way because you might be following that path that way. So that's your direction in which you're going, that direction indicated by the derivative of your path parameterization. And you're doing little bits of that along the way to do it all the way. That's why you're doing an integral of that little bitty work done. Okay. We're done with that, but let's address the reversal. Because if he wants you to do a reverse, the same path but reversed, ooh boy, that's going to be tricky. It's similar to that football thing where I had to like take care of that upper half and lower half, and I have to really figure out some trig functions, how I'm going to express that upper half thing. Similar to that, in the sense that I need to start here at pi. I need to end here at 0. And I can use the same, similar thing, but now my C, I'm going to use C2 for this because I'm doing a different one. I'm done with the problem, but now I'm going to do it in the reverse direction. The rule is you get the negative of that, but I'm going to work it out slowly, and I'm going to talk about how to parameterize this weird one where it starts at pi and goes backwards to 0. I basically need to, that first coordinate is important. I can't put t goes from 0 to pi. I mean, sometimes they go t, and then when they do their integral, instead of doing 0 to pi, they'll do 0 on top of pi. So it'll be going pi to 0. That it works, and it gives you the negative of that, but I'm going to go a little more detail for more versatile situation, and note that what you need here is you need to start off with pi and subtract t. That's reversing the order starting at pi. And we're going to let t go from 0 to pi. So I'm going to let t start off at 0, and I'm going to go the usual direction to pi. So I'm going to go pi over 4. I'm doing some examples to illustrate how it's working. 3 pi over 4, and I'll stop at pi. So I'm letting t go the usual way: 0, pi over 4, pi over 2, 3 pi over 4, pi. And what happens when I actually use this in my x-coordinate? It's going to be pi minus 0, meaning start off at pi, perfect. It'll be pi minus pi over 4, pi minus pi over 2, pi minus 3 pi over 4, and pi minus pi. So that reverses it, starting at pi and then letting t go from 0, means it'll be start at pi minus 0, and then all going to pi, and it will end at pi minus pi. So it does exactly what I want it to. So wherever t is in here, y is still equal to sine of that. So now I have sine of, just like x, and my curve is on sine of x. Y is equal to sine of x, so it needs to be pi minus t. So that right there is the parameterization of that curve going backwards, the reverse direction. And I can use that to do the line integral on this new path, C2. It's a different path technically, although it is just the reverse direction, the reverse orientation of the original path. And I can redo this integral, so that's irrelevant anymore. I'm going to do c prime of t, of 2t. It's going to be -1, and it's going to be negative cosine pi minus t. Alright, I got to redo this integral. I should get -2. I don't need that anymore. That's the old one. But if it's for a fresh problem and you want you to parameterize that curve in that direction, that's our parameterization. Let me write out my line integral formula. This time we're going to do over C2. Still the same vector field, notice, so that didn't change. So it's going to be f of x, y. It'll be y comma y, but y is different now. Right here's my y, so I like that. I have a new x. This is my x of t. This is my y of t. And I'm going to dot product with c prime 2 of t dt. Okay. Alright. So my parameterization still goes from 0 to pi. In the usual direction, I've tweaked my coefficient, my components to make sure it goes that direction on the graph. But I'm letting my parameter just range from 0 to t in the usual direction. My function, it's y comma y. Y is different now. Right here's y. So you're plugging in x and y into this equation. It just happens to not involve x. It could in the future, but here it's just y comma y. So I'm grabbing that. I'm getting sine of pi minus t, sine of pi minus t. Dot product with, oh, I don't have any room. Sorry, let me put some room. And if I wanted to, I could have resolved that with identities. I could have simplified that pi minus t. It simplifies nicely being trig identities, but I'll pretend I'm just going to hold off on that. C prime of t is -1, negative cosine pi minus t, and dt. That's my integral. Rewriting it in terms of a parameter t, and now I'm going to do my dot product. Negative sine pi minus t minus sine of pi minus t cosine pi minus t. And now I want to take a moment and figure out how best to approach this. I could work with that, or I could work out my identities. I'm going to work on my identities, to be honest with you. Yeah, I'm going to work on my identities. I'm not even going to work it out. Identities. Here's pi minus t. Here's t on my unit circle. I'm just going to visually, via unit circle, just pull the identities out of nowhere. Sine of pi over t has the same sign as t. So that's equal to sine of t. That's equal to sine of t. This one. With a negative there. With a negative there. But anyway, sorry. My identities I'm using, based on this visualization of it, is that sine of pi minus t, which is there, t subtracted from the 180 mark, has the same sign. They're both positive, but this way, if they're below the axis, they're both negative. So it's literally the same thing. And you can work it out using the sum difference angles. It'd be sine of pi cosine of negative t, or t, minus sine of t cosine of pi. Is that right? Something like that. But you work it out, and it'll come up to sine of t. I promise you. Yeah, it could be a -1. That's going to be 0. Yep. Okay, let me do my other identity. Cosine. Oh, I can use the same unit circle. The cosine of this is a negative of the cosine of that. So cosine of pi minus t is equal to negative cosine of t. So that one does change signs because it's going to be, if this is positive, that's negative. So I'm going to have those are my identities. I'm going to rewrite this. I have negative sine of pi over t, that's negative sine of t. I have, this stays as negative sine, but I multiply by that, it's going to be plus. So I'm going to get plus sine t cosine t. And I'm going to do that. That's my integral. Okay. Alright, that's going to be negative cosine. No, it's going to be positive cosine. Right? It's going to be antiderivative negative cosine with that negative makes it positive. That's going to be 1/2 sine squared again. And value from 0 to pi. Cosine of pi plus 1/2 sine squared pi minus cosine of 0 plus 1/2 sine squared 0. That's -1, that's 0, that's positive 1, but it's minus that, minus 0. -2 gets you the same answer, but the opposite sign if you just traverse the same curve in the opposite direction, the opposite orientation. So to answer the question, yes, the orientation of your parameterization of H matters. Actually, the path integral depends on the orientation of your... It depends on the orientation of the path. I'm not sure... I don't understand this question. You got to clarify with him. If you reverse the orientation of the path, you get a negative, and it does matter. I don't know if he's asking about that, or if he's asking if you use a different parameterization, because the parameterization they came with, when you parameterize a curve, you have many ways to do it, and your neighbor might do it differently from what you do. When you do your homework and you see bachelor solutions, you will probably have done different parameterizations, but you should get the same answer. So I don't know if he's asking if you just parameterize it differently, does it matter? It does not matter as long as you're traversing in the correct direction. You got to clarify with him that question. I'm not 100% sure what he's asking.